Hello everyone. So let us begin. Now, in this one, we are going to continue about what we did in the last section, and integration and differentiation were almost done. So let me just write down the heading for you. So now we'll be seeing what integrations do we need, because in the last one we tried to do some of the stuffs from statistical analysis and Bayesian interference, and we did MLE, point estimation. We understood how to do the MLE, so I'll just do a recap on MLE first. The MLE is basically maximum likelihood estimator. Now we would like to understand that given a test statistic we would like to know that if this test statistics or the PDF can be maximized, right? So if you have, let's say, f of x1, x2, xn, and this is the joint PDF, and let us say it is also equipped with the parameter theta. This theta is what we call the test statistic here, and we would like to maximize theta. So what we generally do is as follows. So let me give you an example. Now in exponential distribution, we do know that fxx is simply equals to lambda into e to the power minus lambda x, right? Now this accounts for the fact that we can have n random data sets from a random sample, and we can understand that this random sample basically is something we would like to maximize if a joint PDF is given. Now the joint PDF for x1, x2 and up to xn would be The likelihood function is written as L of x colon theta, where theta is the parameter. And obviously this is basically the product of all the joint PDFs we have out there. So we can define it as follows. So this product definition gives you the joint PDF. Now, so this would be the entire result. Now our goal is to do the following. Therefore, what we can do is, right. Now, obviously, this is the function that needs to be maximized, and let us see what pi value of lambda would allow us to do so. So, what we do is, instead of the likelihood function, we rather maximize the log likelihood function, and since the log likelihood function is simply increasing, we get to see the results we want. So, it basically works as follows. Now, using the properties of log, we can distribute the multiplication into summations of logs. So now we need to maximize this, so we differentiate both sides with respect to lambda to get the following. Therefore, so the maximum likelihood estimator basically says that the value of lambda for which the probability will be maximized is basically 1 upon the sample mean, which is basically the answer. Now we understand that this can be done in separate ways, and the embedded videos here will also let you know about all the techniques you need to understand about derivatives and integration, and about exponential distribution and its MLEs. So we are trying to find out some problems, and before that we would need a few results which we try to prove. So result that we need to prove for this section is this: limit of x tends to infinity 1 plus 1 by x whole to the power x is equals to e. Okay, so basically what this means is this can also be rewritten in the form limit x tends to 0 1 plus x whole to the power 1 by x is also equals to e. So both of these limits are equivalent, and we would try to use this result in a few cases. So let us see how to actually achieve that. Now this one is a bit more challenging than previous ones, because we would start off with something we know as the binomial formula. So binomial expansion. Now what is a binomial expansion? So a plus b whole to the power n, this can be expanded when n is a natural number as follows. Like this. So using this we can also find out this expression right here, that 1 plus 1 by x whole to the power x expression, where we know that x is a real number, but for the time being we can actually find out something about it. Like this is also valid for rational numbers and real numbers, but just that we have not done that yet. But we can still use this to find like this, but it would be an infinite series because of the x here. It should be x ck into 1 is irrelevant, so 1 by x whole to the power k, right? Now the thing that is to be noted is this term here. If you just write it as a function of both k and x, it can be written as x ck into 1 by x to the power k, right? Now, how to define this binomial coefficient in terms of rational numbers or real numbers or even negative numbers? So there is a definition. It is same as the one that you define with natural numbers, but just that you do not do the factorial thing here, because factorial makes no sense, right? Because you cannot really find out 0.5 factorial because it doesn't go back to 1. Factorial means that you multiply the integers consecutively until you get 1. But in case of real numbers, in case of rational numbers, that's not how it makes sense. Okay, so what makes sense is this: xck can be written as x into x minus 1 into x minus 2 and all the way up to x minus k plus 1 divided by k factorial. This is the expression, and you have a x to the power k extra in the denominator, which gives us the expression for this. And we are literally trying to find the limit of this expression right here, right? So one of the x's can be cut off, obviously, and what we do get is this: x by x into x minus 1 by x into x minus 2 by x and all the way up to x minus k plus 1 by x. And then there is a 1 by k factorial. And now there are k terms, so I have divided all the k x's in as denominator to this one. So this gives us 1 minus 0 by x into 1 minus 1 by x and all the way up to 1 minus k minus 1 by x whole divided by k factorial, right? Which can be written in the product form as follows: summation r equals to 0 to k minus 1 1 minus r by x, and there is a 1 by k factorial outside, right? Now this definition gives us the notation for factorials, and it can be proved in later sections when we will be discussing about infinite series and infinite products, that this product right here is equal to 1 by k factorial when you put the limit, of course. So when you put the limit, this product is equal to 1 by k factorial into ek factorial, which gives you answer as e. But this product can be evaluated in multiple ways actually, because this product right here has an integral form as well as a differential form, and using the methods of Riemann integration, a lot of times infinite limits can be evaluated, which we shall learn when we get to the integration section, or maybe we can have a glimpse of what's happening, but for now this should work. So this is the basic proof. Now let us do some examples. Example 1: find the limit of sin x by x as x goes to infinity. So basically what we are asking to find is, we can denote the limit by L. So denote the limit by L, and L would be equal to limit x tends to infinity sine of x by x. Okay, now how do we do this? Now this cannot be done because obviously you remember a quite close one where x tends to 0 was given, and if x was going to 0 we knew that sin x by x approaches 1. But here the case is a bit different, and we can clearly see the denominator x, as x goes on to become larger and larger, the denominator becomes much larger, right? And the number should be decreasing by then, the limit value should decrease a lot. But doesn't sin x also increase? No, it doesn't, because we know that sin x for every real value of x lies in the closed interval -1 to 1 for all x belongs to real, right? So this is a property of sin x, that sin x is bounded. Then we can see that sin x is greater than equal to -1, then sin x by x should be greater than equal to -1 by x. Similarly, sin x is less than equals to 1, then sin x by x should be less than equals to 1 by x, right? It is evident that limit x tends to infinity 1 by x is equals to limit x tends to infinity -1 by x is equals to 0. So both the limits actually go to 0 irrespective of the sign, and also since we can bound the function sin x by x using this as we have done here, so we can basically write -1 by x less than equals to sin x by x less than equals to 1 by x, right? Now I'm going to quote a theorem here. It's called the sandwich theorem. It's called the sandwich theorem. It says that if fx, gx, hx are continuous functions, then if fx is less than equals to gx is less than equals to hx, and limit x tends to a fx equals to limit x tends to a hx, and both of them are equal to some alpha where alpha is a real number, then the sandwich theorem states that then limit of x tends to a g of x must also be alpha. So this is the sandwich theorem. That is, the function g of x has been sandwiched in between the functions fx and hx. Okay, so hx is the upper bound for the function, fx is the lower bound for the function, and it is given that the function fx and the function hx, both of them go to some real number alpha when x tends to the value a. So both sides of the limits in which the function gx is sandwiched goes to the same real number alpha, which means that the function in between must also go to alpha, otherwise the inequality would be violated. There is a whole proof for this, but we are not really going to do the proof right now because of the complications, because we need to know what is an epsilon delta definition of a limit. This is completely an analysis course, so I'm not going to code analysis right now unless we need it when we go to the further chapters in probability. So using this we can see that since equals to 0, we can say that limit x tends to infinity sin x upon x must also be 0, since -1 by x less than equals to sin x by x less than equals to 1 by x. Since sin x by x is basically sandwiched between -1 by x and +1 by x. So that would actually solve this problem. So as I said, this is not like a regular problem, but problems like this would be very much evident. Okay, for the next problem I would need a footnote here, that is the footnote of a derivative of a function fx. So derivative derivative of x f of x at x equals to a is defined as, I'll give you the formal definition of derivative for here, and we are going to revisit it when we start derivative, but for this problem this much information is sufficient to do the problem. So f dash a is basically equal to limit x tends to a f of x minus f of a by x minus a. So this basically is the definition of derivative. Okay, this limit, the value of this limit gives you the answer to f dash a. Now the problem, given f of a equals to 2, f dash a equals to 1, g of a equals to minus 1, g dash a equals to 2, then find limit x tends to a g of x into f of a minus g of a into f of x divided by x minus a. So consider the problem. We are given that f and g are two functions which are first time at least once differentiable at the point a, and it is given that f of a is 2, g of a is minus 1, while f dash a, which means the derivative of the function at the point a of f is 1, while g dash a is 2, right? So g dash a is 2 doesn't mean that the derivative of g is 2, it rather means that the derivative of g at the point x equals to a equals to 2. So don't be confused with the definitions and the terminologies I'm using, because it's important that you understand them distinctively. Now limit x tends to a g of x into f of a minus g of a into f of x. What we are going to do here is something like this. We are going to add and subtract ga fa. Minus g of a into f of x, and we are going to draw a line x minus a. Now why did we do that? Because we are going to separate this first two terms and this last two terms and write them as a separate limit. You will see why. Because we want to really find out how to evaluate this kind of problems using all the information given in the problem, and whatever we just learned a bit ago about the definition of a derivative, which you can see here, this would be handy here. So this becomes g of a into f of a divided by x minus a, plus another limit x tends to a g of a into f of a minus g of a into f of x divided by x minus a, right? Now what we can do is we can take the constant common, which is f of a, from the numerator, and we can write this as f of a into limit x tends to a g of x minus g of a by x minus a. Similarly, we can take minus ga common here, and we can write limit x tends to a f of x minus f of a by x minus a. Now if you remember, this was the definition for the derivative of the function at point a, right? So f of a into g dash a minus g of a into f dashed a. This would complete the derivative section for this one, and now it's just a matter to put the value. So fa is 2 and ga is minus 1 and g prime a is 2, so first two terms are 2 into 2. So this gives us the value of 5. So this would actually solve this problem, but as I said, you would need this definition. So once you learn the derivative section, I do not think this would be any more required, but these are the basic things that you should know. Okay, let's move on to the next problem. So we are given to find the following limit. Okay, so this is the problem that we need to find. Limit x tends to infinity, and in the numerator we have root over of x square plus a square minus root over of x square plus b square whole divided by root over of x square plus c square minus root over x square plus d square. Now to do this kind of problems, we, as I said, we need to first rationalize. So let us begin the process. Let this be L. So this is equal to so we shall multiply by this x square plus a square minus x square plus b square into root over x square plus a square plus root over x square plus b square. So this was multiplied, and also we need to multiply by the conjugate of the other term, which is x square plus c square plus x square plus d square. You will see why I did that, because we would need that here. So this thing, first we write whatever there is in the question, x square plus c square minus x square plus d square multiplied by x square plus c square plus x square plus d square, and then the extra term of root over x square plus a square plus x square plus b square. Now once we do the formula, because it's a minus b into a plus b, it turns out as follows. It becomes x square plus a square minus x square minus b square into x square plus c square plus x square plus d square over root. Similarly, in the denominator it becomes x square plus c square minus x square minus d square into root over of x square plus a square plus root over of x square plus d square. Okay, now the x squares get cancelled off in these two expressions, and what we get is this: limit x tends to infinity, a square minus b square by c square minus d square, and now multiplied by root over x square plus a square plus square root of x square plus d square, actually it would be c square, divided by root over of x square plus a square plus root over of x square plus b square. Right? Now we divide up and down by x to get something. So firstly we can take the constant out, and then we can divide up and down by x to get the following: root over x square plus c square plus root over x square plus d square whole by x divided by root over x square plus a square plus root over x square plus b square whole by x. Now this x can be absorbed inside the square root of each term as root over of x square. So once you put the x inside the square root, it becomes by x square, right? So the limit becomes a square minus b square by c square minus d square, limit x tends to infinity. Numerator becomes root over of 1 plus c square by x square plus root over 1 plus d square by x square divided by root over 1 plus a square by x square plus root over 1 plus b square by x square. Now since we know that this individual term c square by x square, d square by x square, a square by x square and b square by x square go to 0 as x tends to infinity, the answer simply becomes a square minus b square by c square minus d square into root 1 plus root 1 by root 1 plus root 1. This is essentially 1, so the answer is a square minus b square by c square minus d squared. So this becomes the answer. So as you see, some of these problems are a bit challenging than before because you might have to do a lot of calculations and you have to be very careful, and then again you need to know the method to do all of them. But if you have learned the third chapter completely, if you know how to rationalize and you do not actually make like imminent errors, I do not think you would be getting this wrong. You might be getting this right every time you attempt it. But the only two problems that were very different with this: first, we used the sandwich theorem to evaluate a limit for the first time. So this is a technique which you are not going to forget now. So you can try it whenever you are stuck at a problem. You can try to bound that function and see if both the bounds yield you the same result at the limiting value of the required function. Then the function itself would be that value. And then again we learned about the derivative of a function and at a certain point and the definition of it. It is called the derivative from first principle when we evaluate it by the limiting definition, and using that we have solved a pretty good problem, I would say. The derivative of a function f of x at x equals to a is given by f dashed of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So what are the derivatives that we are going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sine of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sine b cos a. So this is the formula, right? So using this formula, we can see that sine of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sine a cos h plus sine h cos a minus sine a divided by h, right? So what we can do is limit h tends to 0 sine h by h into cos a. So we can just take the second term here, and we can take the first term common, and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sine square 2 by theta. So using that formula, it becomes minus 2 sine square h by 2 by h, and this limit goes to 0, because firstly sine h by, if it was sine h by 2, we could have found the answer, but since it is sine square h by 2, it goes to 0. So the answer is cos of a. So the derivative of sine of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows. F dash a would be equals to limit x tends to a f of x minus f of a by x minus a, from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula. Now trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula, what we can do is as follows. Using this, we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of a into 1 because this limit is 1 as we have done in previous examples. So the answer becomes minus sin of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: h tends to 0 f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1 as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself.
So let us just quickly recall all the things that we have learned. So I'm going to write down the things we have learned in both limits and derivatives one by one. So just to recall and have a review of what we have learned. So this result, as you remember, it was limit x tends to a x to the power n minus a to the power n by x minus a equals to n into a to the power n minus 1. These two limits are almost the same kind of limits because, as you know, when we proved them using the Taylor series expansion of the functions log of 1 plus x and e to the power x. So that's why I'm writing them simultaneously. So these two limits were also there. Then we had the limit involving the sine function, which was limit x tends to 0 sin x by x equals to 1. Now we have improper limit as follows. And this is equal to the exponential number e. Right, so this completes the basic definitions for all the results on limit. And now the definition of derivative, just to recall. So the derivative of a function at x equals to a is given by f dashed a equals to, there are two definitions, I'm going to write both of them. X minus a, this is in turn equal to limit h tends to 0 f of a plus h by h. So these are the two definitions that we use in order to find out the derivative of a function, which we also did in the last lecture. We found out the derivatives of e to the power x, sin x, cos x, and in this lecture obviously we are going to learn about the chain rule, and that would actually change the way we look at derivatives. It would be pretty easy now to evaluate derivatives using what I'm going to tell you. So this was done, and we also did a few basic derivatives like ddx of sin x. So anyways, now we can try and find out the derivative of, so we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax, so first recall the basic function. The function, what it starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only, and write the whole function down, but then multiply it we go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x, and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now, how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now, the answer can be written directly if we have that in mind, because we differentiate one by one, and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it was the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 of the is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x, e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x because the differentiation of a constant is 0. And if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x, so 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x, so 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously it's a multiplication in between. So this is our final answer for the problem. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives, There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.